like to thank the organizer of the series. Actually, I'll stand closer to the computer, so if you want to continue. But yeah, I'd like to thank the organizer for the series, for the invitation to talk. And I will talk about a few things and how they're connected. I'll also go into a little bit of the technical details so that people who are interested in them can learn something. Let's get started. The work is based on two papers, one from last year and one from last month. Right. So to begin with, I will talk about something that's seemingly disconnected to the topic, but I will very soon see how it's related, and which is called OTOC. And then we'll mainly focus on post-skipping, and I'll talk about post-skipping from the definition, from the methods, etc. Along the way, I'll talk about how it's connected to the other topics in the title, such as quasinormal modes, shockwaves, and chaos. So that's the plan. So to begin with, let's talk about this OTOC, which stands for out-of-time order correlator. So usually, OTOC, out-of-time order could be endpoint function as long as it's not time ordered. But here, in the context of chaos, people usually are interested in this specific OTOC. People usually also say the OTOC, which is a four-point function where you have two operators at t and x, and another two at a different time and location, which by symmetry we can put it at the origin. So I won't go into detail of how and why this takes a specific form on the right, but for large N-gauge theories and actually for slightly more general quantum many-body systems, you can show, and either numerically or from using some other methods, it takes this generic form, where it has a constant part, which is not interesting, but then it also has an exponentially growing part, which has a exponent, which we call the Lyapunov exponent in front of time. And then there is a time offset that is called scrambling time. There's also a spatial dependent offset, and with a characteristic velocity, which we call the butterfly velocity. So roughly speaking, this Lyapunov exponent tells you how in a given quantum chaotic system, a small perturbation grows in time. And this butterfly velocity, roughly speaking, tells you how this growth is offset, given how far away a little perturbation is from the point you're interested in. So suppose we think of this W as the perturbation, and then V is like a sort of a test at some other location T, other location X, and some other time T, to tell you about how to help us understand how the effect of this local perturbation is propagating in time and space. So the takeaway here is there are roughly speaking, three characteristic parameters that will tell us about the general behavior of a general quantum chaotic system. And these two parameters, the Lyapunov exponent and butterfly velocity, will be in particular interesting to us. Another comment about this butterfly velocity is of course smaller than the speed of light, and for these systems, it's actually more important than the speed of light for many reasons. One reason being that even though the theoretical upper limit for information transfer or propagation is the speed of light, but effectively you actually are bounded by this butterfly velocity. So that in terms of information and scrambling, etc., that is a more physical and relevant. So was there a question? If not, let me continue and say that.
How close is it to the speed of light? No.
Oh, well, I guess how close is a hard question to answer, because I don't know if 90% of the speed of light is close to the speed of light, but it really depends on the system. So it could be much lower than the speed of light, but depends on the microscopic details.
And this behavior with time is for large t, or?
Okay, so this dependence on time is it has to be it's usually early time. Early time here in the sense of before everything saturates. So if you have a for example, a compact space. And then after a while, everything will thermalize and then will reach equilibrium. So in a sense, you don't want too late time to look at this behavior. But it's not also too early time because it sort of it starts off a little bit theory dependently, and then it has this universal behavior after a while. Usually the scrambling time is the relevant scale to see this behavior. Another comment about this butterfly velocity is there is this information, spread. Okay, let me also before that say that because there's a characteristic velocity, and what is relevant here is called the butterfly cone, and it's of course narrower than the speed of the light cone, and is more important. And the funny thing is there even for non-relativistic systems where, sorry, that's relativistic, not realistic, non-relativistic system where there is no speed of light. So for those systems, you don't have a speed of light to bound your information propagation, but then the butterfly velocity will be helpful in that sense, in that case. So that's the very quick overview. And now let's talk about how this is realized in ADS-CFT or holography. So
sometimes non-relativistic systems have relativistic fixed points. Have fixed points with Lorentz symmetry. Does the butterfly velocity then come into the light of essentially?
That's a good question. So even for relativistic theories, it's generally smaller than the speed of light. Usually it never equals the speed of light.
But sometimes you start out with a non-relativistic system and you go to some point, it's quite common that you'll get relativistic symmetry. And is the speed there?
Yeah, I'm not sure. I don't know, but yeah, but if that happens, it has to be a special thing about this particular non-relativistic system in this particular limit. But it's not generally true for a general relativistic theory. I'm sorry, was there a question? I couldn't hear it clearly.
No, someone was just muted.
Oh, yeah. Okay, thanks. All right, so now let's come
about the OTOC. So you said in large N gauge theories it has this sort of universal form, but I mean, did people actually compute it in some specific large N theories? It's like a strong coupling calculation, right? So it's like you could compute it in things like SYK, but
yeah,
for large N gauge theory, when you said that, you really meant in the gravity side. That's the prediction, and that's like expected of the field theory. Or
usually such statements are made in the bulk, but in this case, people actually do more calculations on this quantum boundary systems. But if you ask me whether it's actually in the strictly strongly coupled limit and with actually large N, I'm not sure. But there's a lot of computation either in lower dimensional models or even some high dimensional models.
Right.
Yeah, so it's quite universal, and the thing I said actually goes beyond the holographic systems. But in holography, there is a very simple realization of the calculation of OTOC. I won't go into all the details because there are a few logical steps here I won't have time to talk about. But roughly speaking, you can think of, if you go back one slide, think of this 4-point function as the inner product between two states, which I write here as these two. So now if you understand the two states, and then you can try to imagine how, how big the inner product is, then there's give you some sense of how this OTOC is big or small. So in particular, one state would be that if you start with the thermal state, you insert some operator at 0, which would be the green one here. And then you insert some another operator at minus t, where t is large. In holography or in the bulk, if t is large in the large t limit, and then this particle that's that's sent from the boundary to the bulk will be infinitely boosted due to the horizon of the black hole. And in the large t limit, it becomes a shockwave, which is the exact solution of GR. So once you have that, and then you look at how this green particle would change when it passes through this shockwave, it will get shifted. So the final sort of state for this green particle would go along this trajectory. Whereas the other state, you do the opposite thing. You first create this shockwave, and then you insert the other green particle directly at t equals 0. So because you're inserting it at t equals 0 at the end, you have to propagate it into the future and into the past. So unlike the other case where you think of this as preparing the state, here you just impose that it is located at t equals 0. And now if you compare these two trajectory, it will have a different the overlap between the two states will depend on how much this shift is. If the shift is super tiny, then the two states essentially have a close to 1 inner product. And of course, if it's big, it's small. And the funny thing about the shockwave solution is that this is dependent on the transverse direction x, so which is not shown in this picture, but it's the transverse direction. And we're also thinking about a planar black hole, just for simplicity. So in that case, you see some x-dependent shift, which means the inner product will be x-dependent, although I'm not explicitly writing x here. And then going back, we know that the OTOC will depend on x. And just by comparing this ansatz with what you actually get from the shockwave calculation, you can extract the butterfly velocity, Lyapunov exponent, etc., from the bulk calculation. So roughly, to summarize, the OTOC can be calculated in the bulk using the shockwave solution. Yeah.
So you said we need to take the large to limit for holography. How does that then compare to the scrubbing?
How does A will have to be at the order of the scrambling time, which is a regime where this sort of ansatz holds. So I would say if you want to be really precise, it has to be on the same order of scrambling time, but it shouldn't be too large so that everything thermalizes. So yeah.
So the scrambling time also has to be big enough compared to.
Oh, no. Here, the scrambling time, it depends on the number of okay, so I didn't say this in the non-holographic case, but if you actually do this computation in a boundary system, the scrambling time depends on n, and so it scales with n. In the bulk, it will be because we're looking at the sort of large n limit, it will be large. Yeah, if it's not large, then I would say it doesn't give you the limit of a shockwave calculation. It's more general. Yeah, so that was in a sense the classical bulk calculation. And for people who are interested in the details, I'll just very quickly show the steps to if you want to go about doing this calculation. And in fact, I want to present it in this way so that it generalizes to beyond Einstein gravity. So although I'm presenting the result for Einstein gravity. So what you do is to start with, this is a regional black hole solution to set it in Kruskal coordinates. And this is ansatz of the perturbation you have to add if you want to solve the full Einstein equation. Of course, you can add other perturbations, then you see that it doesn't solve the Einstein equation. So you can include this perturbation in the metric, and then you also want to make sure you actually source this perturbation. And the thing to do here is to have a localized source in X. So think of this as a point like a perturbation on the boundary, and that will support the stress tensor in the bulk. And by sort of expecting that everything localizes on the horizon, we can also give it a delta function on the horizon to localize it on the horizon. So that's just ansatz. Of course, the first time people discover this is not using this ansatz because they don't know what ansatz to use. But now, with hindsight, this is what you can do. You also make ansatz for this how, for example, the unknown function depends on x, where r here is the modulus of x. Here, once you have everything, you just substitute everything into the equation motion. It turns out that once you have this ansatz, all the equation of motion, all the components of equation motion are automatically zero, almost by, well, not almost, by symmetry, except this one particular component, which you do have to solve. And as long as you solve this equation, it gives you it determines the unknown parameter in this ansatz H. And here, because you can see that there is a time dependence, a spatial dependence, and then you extract the velocity from this ansatz. And that, if you go back to compare the OTOC expression, you get the butterfly velocity in Einstein equation in terms of some metric components of the black hole solution. And if you repeat this, you get a different butterfly velocity depending on what theory you are in, right? So if you have a high derivative theory, you get a more complicated expression, which I'll show in the next slide.
So you have on top of that wave metric, you have a black hole in the background. Is that what we're doing?
Oh yeah, sorry, I should say that. You start with a black hole. You put that
wave on top.
Yeah. Well, actually, sorry. I think I didn't specify what A and B's are, but A and B describe they have the property that it describes a black hole. So this is the perturbation on top of a black hole. Yeah, I should just.
The plus 2 bits of the metric are a black hole and correspond.
Yeah, that's right. That's right. We need, for example, A to vanish when UV equal to 0 as the Kruskal result. Sorry, though, we want well, you have to
black brain kind of thing with
exactly. It's a planar black hole or black brain, if you like.
So A0 is the value of A without the perturbation?
Without the perturbation, yes.
And B1?
Yeah, is the first
correction.
Sorry, no, it's still for the background solution. Is the coefficient of the Taylor expansion around the black hole. I didn't want to give too much details, but yes. So they are both parameters of the background solution. So if you repeat this, you can, for example, for F Riemann gravity, which is a very huge class of higher derivative corrections, where the Lagrangian is an arbitrary number of Riemann tensors contracted in arbitrary number in whatever way you want, as long as it's diffuse invariant. Then you can do this computation, and it's very complicated. In general, for example, we still have B1, as you're asking, the Taylor coefficient, but then you also have A1, B2, etc. So, but everything is near horizon, right? So it depends on the near horizon expansion of the metric. And these quantities, of course, depend on the Lagrangian. It tells you how the choice of Lagrangian determines the butterfly velocity. Yeah, question.
In the original setup on the field theory side, are you thinking about the pure states or mixed states, or that's not really?
Okay. So far, everything is in thermal state. So you can think of it as a mixed state. Because this is how it's easiest to see, for example, the temperature dependence, and also just general expectation that the black hole is due to a thermal state in ADS-CFT, and we don't see this in a non-black hole geometry. And for pure state, you also don't really expect chaotic behavior. But of course, depends on the system. So that was the reason why I'm presenting this result for the high derivative will become clear in a little bit, because it will become clear.
Sorry, beta mu or what? So the final formula is
yeah. So good. So
beta is the temperature.
Beta is the inverse temperature.
And mu is the coefficient of the coupling.
Mu is actually just the unknown parameter in the ansatz. So I could have just not defined mu and put the butterfly velocity here. But this is, so in some sense, a definition of mu and also definition of butterfly velocity.
Wait, I thought you were computing butterfly.
Right. So you can think of this as one quantity. So once you know what mu is, you know what butterfly velocity is. And
I would figure out what
mu is the solution to this quadratic. You see here you have mu squared, mu to the fourth. So it's quadratic equation for mu squared. Once you solve for the roots of this f equal to 0, you get solutions for mu, and then you get solutions for butterfly velocity. It just yeah, just an extra step I'm not presenting.
Okay, what they can't, like, they can't feel that well, but what is the mu a function of?
Oh, good. Mu is a function. In this case, if you try to solve for a solution, it will depend on all these parameters, and they are functions of the Lagrangian. So at the end, my Lagrangian will have, you know, like an Einstein piece and then high derivative corrections. And when
It's a function of the higher derivative, correct?
Exactly.
What is it if there aren't any higher derivatives?
Oh, then we just get Einstein result, which is simple.
Right.
Yeah, which is okay. It depends. In general, it depends on both the metric expansion coefficients and the high derivative couplings. Of course, if you don't have high derivative couplings, reduces to the simplest case, which is the Einstein gravity result. It also depends on the space-time dimension. With high derivative coupling, you just get a more complicated result.
I would have thought Einstein gravity would just be 1 over beta times a pure number.
1 over beta. Well, I mean, this is in some sense a pure number if you have vacuum Einstein gravity, in which case you know what A0 and B1 are. I'm sort of generalizing this so that the solution could be a black hole supported with matter fields. Then it's not necessarily Schwarzschild ADS. It could be like perturbation to that.
But it depends on the solution only that you started with.
Exactly.
Whatever that is.
Exactly. Whatever that is, you have a black hole. We do require that to be stationary so that it computes some thermal equilibrium state 4-pound function. Other than that, it can be a general black hole solution. So that's why I'm not.
In the higher derivative case, you need the solution to solve the higher derivative Einstein equations, or do you?
Yeah, it's a good question. So for consistency, sure, we do need to do that. But at this level of the math, we don't use that fact.
Yeah.
We just keep it general. And yeah.
Presumably, you're just working the first order in the higher derivative problem.
Yeah, I would say mathematically, not yet. We haven't used that fact. But if you wanna, if you wanna say that, okay, my background has to solve consistently order by order, and then presumably it only works if you have the depends on how well you can solve the background solution to high order in coupling constant. If you can solve it order by order, then this is true order by order. But if we don't have the solution to higher orders, then this has to be linearized around that Einstein result. Yeah, but at the level of this calculation, where we don't use the fact that it solves the new perturbatively high derivative equations motion, it's a non-perturbative in the coupling constants.
So f mu equals 0 is a consequence of the Einstein equation, right? It's a function.
Is the okay, good. This is the result of setting the linearized equation motion to 0. However, shockwave, it turns out to be, even if you just solve the linearized equation motion, it turns out to be a non-perturbative solution. So if you look at the second order, correction, once you substitute in the perturbations, it's automatically 0. So, even though we're looking at the linearized corrected high derivative Einstein's equation, it's a nonlinear solution. So that's why,
But it's a nonlinear solution to a theory that doesn't make sense from here.
Yeah, I mean, perturbatively to each order, if you like, to the coupling constant, it could mathematically make sense. So for example, if we correct it at first order, thinking that makes sense, and then we can look at the next order. But I agree, non-linearly, non-perturbatively, that's not probably not the thing to worry about. So now we'll sort of talk about slightly different thing, and the things I reviewed will be relevant very soon. So just to say what postskipping comes from, or why it's relevant, is a property about the retarded Green's function. So this again doesn't have to have a holographic bulk description. It's again a thing you can discover just from some many-body quantum chaotic systems. if you look at the retarded Green's function, usually it takes the form of B over A, where B is in a sense the response to some perturbation A. In holography, the source A is realized as a boundary conformal, in terms of in the case of the metric, is a conformal metric. In general, it's just some leading order expansion coefficient of the fields near the boundary, where z equal to 0 is the conformal boundary. And B is realized as some subleading Taylor expansion of this whatever field we care about. It could be the metric, it could be the Maxwell field, it could be scalar field, and whether the power of these powers will depend on what we look at and what theory we look at. But in general, it's always like that. So in some sense, once you know the full solution or full field configuration of some field we care about, which is X, then we can read off A and B just from doing this expansion. And on the inner horizon, on the future horizon, we also impose ingoing boundary condition that's related to the fact that we compute a retarded Green's function. If you compute advanced, then you put outgoing on the past horizon. So once you do that, it's interesting now that B is determined from A. If you don't do that, actually this will be two independent degrees of freedom, because if you just look at if you just do expansion of some fields near the boundary, and because you generally have two second order differential equations, and these two are not related. But generally, if you take them to be independent, it's not going to satisfy the boundary condition at the inner horizon, at the future horizon. So that's why this extra ingoing boundary condition will help us determine B from A. Once B is determined from A, if you take the ratio, and then you can calculate the Green's function. That's how how the holographic Green's function is computed. So now the funny thing happens when this is what was called postgaping. So it happens when you have both A and B equal to 0. So A equals 0 means there's a pole in the Green's function. B equals 0 means there's a 0. And postgaping happens when they're both 0. So this Green's function actually takes the form of 0 divided by 0. And that limit is actually not well defined, because if you actually try to approach this limit, you will see that the result is multi-valued and depends on how you approach this limit. And that's when they first discovered postgaping. That's only like 5-6 years ago. And they found this example in Einstein gravity. And the reason why, this is a very simple calculation. The reason why people didn't find it before that is really because here, this weird thing happens at some imaginary wave number and some imaginary frequency. If you have the imaginary wave number, if you go back to this ansatz, you'll see that it will grow exponentially along one of the directions in X, and that's usually not considered for physical reasons. But whenever you do this calculation, you can always analytically continue. So even if it's this particular growth may not be physically relevant, but it is a property about the analytic structure of the Green's function, which in many cases people do have. They know the analytic expression, and then they can just analytically continue K and omega, and then they exactly discover this behavior. Why is that interesting? I mean, it's possible that other people found it, and it just happens, and nothing interesting comes out. However, the very first example they found was already very interesting because it happens at a particular omega and K that's related to the parameters we talked about earlier. In particular, it happens at this Lyapunov exponent for when the imaginary omega is there, when the imaginary K is is Lyapunov exponent divided by butterfly velocity. So that butterfly velocity is exactly what what was calculated earlier, what I presented earlier. And then a simple question to ask is that a coincidence? It could be just as Andy was saying, it's just a number, right? So if two two results agree that both numbers may be just a coincidence. But then it has been checked that the fact that it happens exactly at this location holds also to Gauss-Bonnet gravity and while to the fourth gravity. So in some sense, it's in something there are two independent ways of calculating the butterfly velocity, and they agree, at least in these examples. So to explain that, this paper provided a more sort of a near horizon gravitational explanation by realizing that at this particular frequency and momentum, if you look at the relevant Einstein equation component, if you substitute this in, here I'm writing the Einstein equation by already Fourier transforming all my perturbations. If you look at this Einstein equation, it actually becomes trivial in the sense that all these coefficients become zero. You can check. When it becomes zero, that means this Einstein equation just doesn't do anything. It doesn't constrain these perturbations. In other words, we're trying to determine, if we go back a little bit, we're trying to determine B from A. However, now B is not determined because we're losing one constraint. We have fewer constraints than the degrees of freedom. So we don't have a unique solution. And when the bulk solution is not unique, and because we're computing B over A, which is now ambiguous, the Green function is ambiguous. And that explains why, why this funny thing happens in the Green function. And just another comment, which is over the years that what I said in the previous slide has been discovered, people realize it not only happens at that particular frequency and momentum, it happens more generally. It happens at, this is a calculation for scalar field on top of a BTZ background, where they know exactly they know exactly what the Green function is. So you can just look at the lines of poles and the lines of zeros. And when they cross, you get 0 divided by 0. And you can check that exactly at those points, there is an ambiguity in the Green function. So there has been a lot of work on this, and it is said that this is a very powerful constraint because you have infinitely many constraints on the structure of the Green function. And in general, even if you don't care about it as CFT, these are powerful constraints on the quasi-normal mode spectrum, so that there has been a lot of hope in trying to reconstruct some properties of the bulk just from these knowing these locations of pole-skipping points. And these are very simple to compute, which I'll talk more on the next slide. So in some sense, there's an alternative way of getting a lot of information about the theory or the spectrum or the Green function without doing the hard computation. Sometimes it may require a numerical methods. Here is analytical and quite simple. So now sort of trying to summarize and also to organize everything I've been saying about pole skipping. So this will be a little bit of a generalization of everything that's been said. So I'll go over this more quickly than the previous slides because it's getting more technical, but I just want to show sort of what's involved in this technical part of the formalism. So what we did here is to forget about what theory we have for now. Let's not choose a specific theory. Let's just use symmetry and see how much we can already say from symmetry arguments. So here, let's begin with a black hole solution in the ingoing anything-Finkelstein coordinate. That's a good coordinate for describing the future horizon and also for describing quasi-normal modes. So that's what we'll use. You can define a weight for any tensor component to be the number of lower V indices and minus the number of lower R indices. And why is that relevant? I'm not showing that, but that's roughly speaking counting how much a tensor component transforms under a boost transformation or a boost symmetry. So with the boost symmetry and with this definition of weight, it's easy to show that any quantity component of a tensor that has a positive weight has to vanish on the stationary background. It's important it's a stationary background because that's when you actually have the boost symmetry. So we don't require that for the perturbation, just for the background. But that's enough for our purpose. So the general postgaping, or the general method for sort of working this out is to just very generally write in any theory, organize the equation's motion by writing the perturbation of the equation motion and relate that to the perturbation of the metric or the fields we consider. And we can write that as a matrix because now we've defined weight. So we can organize it weight by weight. For different weight P, there's relation between the relevant quantity that appear in this equation motion. So in some sense, we're writing the same equation, but we expand it order by order and give every component a different weight. And then we're going to use the following fact. That is, once you write the equation motion in this way, all the important information is in this M matrix because these are just perturbations. So it's easy to show that for P greater than Q, this matrix will be proportional to a bunch of factors dependent on the frequency and the weight. And this is, roughly speaking, the proof. It involves sort of looking at covariant derivatives and also Christopher symbols. Yeah, I'm gonna skip the details. But once you show this fact, already many things become clearer because this is a full equation motion matrix. So for given P or given Q, it's just one entry in this huge matrix. And using this fact, we can already see that, for example, if we set the frequency to be Q0, which is the highest weight appearing in this theory, if you set to be Q0 minus 1 times this number, by this property, it sets everything in this purple box to 0. And once you've done that, remember that the remaining thing so we've chosen a value for omega. We still have k to play with. So we can generally set the determinant of the remaining square matrix to 0 by choosing a value for k. Once you've done that, you can see that this set of equation motion is already, in some sense, non-invertible, in the sense that the linear combination of them is trivial. So that's going back to what we were saying earlier about, a particular equation motion becoming trivial, and then it's not enough to determine the bulk solution, which makes the postgaping happen, which makes the Green's function ambiguous. And in fact, you can keep doing this. You can choose this to be a different frequency. You can choose Q0 minus 2, and that will set another set of entries to 0. And then you just have to require the remaining combination of these 4 squares at this huge square matrix to have a determinant being 0. And then one of these sets of equation motion will become trivial. And that's another set of postgaping points because for the same reason. And now you can keep doing this, choose a different frequency, and set this huge square matrix to have determinant 0. So you can keep going. In fact, for any positive S, which I write here, you have a set of ways to make the equation motion trivial. And here, the MS denotes whatever that remains after you set everything to its right to 0. So that's the general postgaping condition we derived. And that's useful because now there's a systematic way, given any theory, to compute these postgaping points. I mean, I guess there's a question of what you need from it and how useful it is. But people do compute this using very different methods prior to this work. And they usually have to look for a particular combination of the equation motion and play with the gauge conditions, etc., to make sure it works. Here, this is quite general and it's very systematic. That's the point. You don't have to worry about the theory. Just write down all the equation motion, do expansions, and do this procedure that allows you to find all the postgaping points. So, what's more interesting to us, like to someone who doesn't want to know the details and exactly where the postgaping happens? Well, there are already a few conclusions and applications we can draw from this. For example, if we look at the leading frequency where postgaping happens, and that's when S equal to 1, the smallest that's allowed. Then this omega equals that, and then this particular quasinormal mode will grow like e to the q0 minus 1 times 2 pi t times v, the retarded time. But if q0 is greater than 2, and then you will get a growth that's greater than the maximum allowed value for a unitary chaotic quantum chaotic system, which is just 2 pi t. So in some sense, this already suggests that if your theory has q0 greater than 2, your theory is too chaotic. In other words, it violates the chaos bound. But when does q0 is greater? When does q0 exceed 2? That's exactly when your theory has spins that's higher than 2. For example, you have spin 3 field, spin 4 field, and those are known to have problems. Those are known to have causality problems. Those are known to have chaos violations, etc. So this is just another way to see that or to show that these theories are terrible. Of course, it's known also that if you have infinitely power of high spin fields, then it may be okay. That's not inconsistent with this conclusion, because in this formalism, we do have to have an upper bound on the spin. So I'm talking about the higher finite spin in the theory here. If you have infinite, this argument doesn't work.
Did this formalism again assume anything about the bulk Lagrangian? Like you assume that you still have Einstein equations plus stuff, but some generic higher spin theory might not have that space-time.
Yeah,
describing.
I agree.
What was the assumption that went into?
Yeah, so I guess here we're being very abstract. So
Right.
I guess it's there is a question of whether if you just have a diffuse morphism invariant theory with high spins, can you still have a black hole solution, etc.
Yeah.
Then I don't know. But then the conclusion could be that if you have a black hole solution to that theory, then this holds. Alternatively, you could say, okay, I'm going to still perturbatively go away from Einstein gravity, where I know things are okay. And then if you just perturbatively add high spin fields, we would assume that at least the original solution in Einstein gravity will just be perturbatively corrected. And then already you will say that this causality and this chaos bound will be perturbatively violated. There's a different way to interpret that. And
from the bulk point of view, does anything go wrong? I mean, the chaos bound would be a statement about some dual theory, right? But
yeah. From the bulk point of view, just from this calculation, it's not too clear what statement to make, but already you can say that there exists some quasinormal mode that grows exponentially in time.
Okay.
That's and too exponentially in some sense. So that's how to see it's bad. And then you can say, okay, let's forget about high spin. Let's just focus on spin 2, just high due to gravity. But where we know at least perturbatively everything's okay and not violating chaos bound, etc. If you do that, and then the leading post-skipping, as we argued, is exactly at this point, which is maximally chaotic. And if you just set the leading matrix to 0, the determinant of that to 0, it gives you the exact value of k, and that will agree with what's calculated from the OTOC. I haven't explained why. I have more equation on next slide, but this is the conclusion. So earlier we were saying that, okay, it's discovered and checked in examples that this leading post-skipping happens at some point related to the parameters of chaos. Here I was saying essentially from this formalism, it's very easy to see and prove that's always the case for arbitrary high degree gravity. And just another side comment, we also showed this for fermions, where Q0 is a half integer. So you just have another set of post-skipping points if you see we have fermions. And we can now go back to the picture we had earlier from some paper on the BTC calculation. And you can check that all the points satisfy our or like fit into this formalism, because we were saying that there's a spacing at integer multiples of this for the frequency, and if you look at that exactly, that's what is happening. And the leading one is when Q0 minus 1, and here they're computing the scalar Green's function. So Q0 is 0. So the first one happens at minus I 2 pi t, and that's why it starts from here. So everything is consistent, and just a check. And also, there's more if you go to lower frequency, just because we are computing the determinant of a larger matrix. There's just more values to more solutions to that equation. So this I will not go into details, but roughly speaking, this is how you would go about showing exactly why this post-giving happens at this point related to butterfly velocity. It's actually very simple. It just involves some change of coordinates. You go from ingoing to the cruise score coordinate, and then there's some property about the delta function and distribution. So at the end, you have a proof. That's generally the case. So what was discovered actually is not a coincidence. It's always true, and it's you can think of this as a agreement between two independent definitions of the butterfly velocity. And another more physical explanation for why these two agree, but this is slightly a more, I would say, more of an argument than a mathematical proof. But roughly speaking, you could regularize this particular quasinormal mode as the frequency and momentum, which we know happens to be related to chaos. Just regularize that quasinormal mode and then take some limit, and then we see that it looks like a delta function, it looks like a delta function. And if you take the limit, remove the regulator, it actually becomes exactly localized at the path horizon. That's when we get the shockwave. So this is sort of a physical connection between the quasinormal mode and the shockwave. I should say that usually people didn't use this language because of the unphysical property about this quasinormal mode, because it grows exponentially in the spatial direction. And that's usually why people exclude them from being part of the quasinormal mode spectrum. But here we're saying that we relax that condition, we allow the quasinormal mode to grow exponentially in space. If you do that, then you can discover some interesting thing. For example, the shockwave coming from a limit of this particular quasinormal mode. Any questions so far? So that's essentially it. I think there are some interesting comments I want to make, and some discussions. So I'll quickly go over that. But a lot of this sort of open questions, so I would be happy to talk more about this afterwards. The summary is really we've given a general post-giving condition, right? So you can do this now systematically given any diffeomorphism invariant theory without sort of doing what people usually do, which is to explicitly write down the equation motion, try to substitute into things and try to find linear combination that works. But here we're phrasing it in a more covariant way, so that you just look at the determinant of some square matrix, and you don't have to worry about the theory at all. And you can also make some general statements about what's the leading post-giving point? Is that related to chaos? Is that related to spin of the theory? And even it turns out that everything works is related to the highest spin in the theory, either fermionic or bosonic. And if the spin is too high, higher than 2, we actually get a chaos bound violation. So this is the kind of thing that's you could check example by example without this formalism. You can check spin theory and explicitly see that you get this violation. But now we're making an argument without knowing what explicit Lagrangian the spin theory has. As long as it has a spin theory field in it, then it will have to be ultra chaotic. Another thing that's relevant, interesting for people in this community is that now it's a proof that butterfly velocities actually match two independent definitions, give you exactly the same answers. Another thing we just said is that there is this nice connection between the two, very physically at the level of the metric. So you don't even have to worry about the theory. This is a statement about the metric itself. And so just to another application of this would be that now I've talked about two ways of defining the butterfly velocity, and they actually agree, which we just said, for arbitrary high derivative gravity. But there's another way of independent way of defining butterfly velocity involving using the RT surface or Takeyanagi surface in ADS CFT. In that, there's no proof that this third definition is exactly agreeing with these two. But by some explicit calculation, at least for a huge class of theories of Riemann gravity, they do agree. So it'll be interesting to actually prove this for more general theory and see whether there's a deeper connection between the three. And I would say this is very interesting because at least for shockwave and postscaping, there are both properties about the perturbed, equation motion on top of a black hole background. So in some sense, I would say both of these are dynamics of the bulk theory. But here, this would be slightly more interesting because it doesn't really care about, it doesn't even use the equation motion. It uses the RT formula, which is it's about the entanglement structure of the boundary theory. So in a sense, some people like to say this is in the same, sort of general slogan of entanglement builds space-time, right? So there is some entanglement formula for high duty theory that knows exactly the same as this dynamical equation motion knows. So in some sense, probably this is a deeper connection than this connection we just showed. This is the final slide. I think I'll just spend 1 minute going through the points and then I'll stop there. So first, might be interesting to do the zero temperature. It's usually known that if you have the non-zero temperature and if you take the smooth limit appropriately, you just get the correct result. But then there's a question of how to take this limit appropriately. Because if you just naively set t equal to 0, and then as we just saw, there's infinitely many postscaping frequencies that are proportional to t with a different proportionality constant. Now, if you set t equals 0, all these different layers of postscaping will collapse onto the same layer, and that's a problem. And also, it's known that some poles in Green's function become branch points in this limit of t equal to 0. So you have to do this very carefully to generalize this to zero temperature. And also rotating black holes, I think it's known from examples that everything works for rotating black holes. But the formalism, for simplicity, we have restricted to non-rotating stationary planar black holes. So for that reason, there's still a mathematical question of how easy it is to show that, even though the examples seem to suggest, everything still works. And this is another thing I commented on a little bit. If you have infinite many spins, this formalism doesn't work because we have to start from some highest finite spin. But that's great. That's great because for infinite many spins, actually it's known that, for example, Vasilev and some higher spin theories in the bulk, they're due to a free theory on the boundary where there is no chaos, right? Then if we predict something chaotic for the boundary, it would be bad. Now it's great because there's no inconsistency. However, yeah, that's another way. That's another way to make everything consistent. Yeah, so in some sense, this doesn't say anything about those theories. But people like to ask the question of, still whether there is a way to at least focus on one higher spin field, do some analysis, and then add all the contribution from all of them and see if you can get, in a sense, a resummation of all these seemingly sort of chaotic and ultra chaotic behavior, but somehow they all sum to 0. That's like a hope in this community. People have been, I think, Mark Mazet, Hong Liu, and other people have come up with effective models to show that. But in some sense, in those models, it's by construction. It has to reproduce the fact that if you resum infinite many spins, you get a finite that's Lyapunov exponent that satisfies the bound. So there's no intrinsic independent calculation beyond EFT. There's actually a lot of work already on non-holographic postscaping, so I won't say too much. And another interesting thing is because I sort of showed you that for gravity, if you have quasinormal mode at this particular frequency, we take the limit, we get a shockwave. But it seems that mathematically, at least, everything still works if you have a high spin quasinormal mode. In that sense, you just have to see if you can take the limit in the same way and get a higher spin shockwave. It seems to work from examples, but there's no general argument yet. Also, relatively, can you have, if your highest spin is fermionic, can you do the same thing? And that is not too clear to us. I don't have too much comment on that. And finally, whether this is sort of a formalism that allows you to constrain some universal property of the boundaries holographic CFT. And in fact, it seems quite for this kind of universal behavior, everything only depends on the near horizon geometry. So where you know what the symmetry is, and you can do a lot of symmetry arguments and constraints. So the more general question is, are there other things you can constrain for the holographic CFT just from the near horizon geometry? There are probably many candidates, and but there hasn't been too much work on that. I think I'll stop there, and thank you.
All right, let's thank Diandian for the wonderful talk. So if anybody has any questions, I guess we go to in the other time. So if anybody got any questions, like you can talk to Diandian about it in person, right?
Yeah.
Nice talk.
Thanks.
Thank you. Yeah.